Welcome to the next part of the lecture. Now we continue our discussion with continuous random variables, and accordingly we can define mutual information for continuous random variables. Okay, so now suppose you have a sender or transmitter X which is generating some information which is continuous in nature, that is, it takes continuous values as some density function px of x. It is transmitted over some communication channel, and what you receive is y, which has density function fy of y. Now if I want to define now mutual information, okay, let me first recall here the mutual information of discrete case. Suppose you have x and y, they are both discrete. X has probability mass function px of x, y has marginal probability mass function py of y, and their joint distribution is pxy of x comma y. Then you know mutual information fundamentally is defined in this way. So you take log ratio of joint distribution and product of marginals. So in one way you can say that it is the comparison of x and y are not independent, they are dependent on each other, so they will be described by joint distribution, versus the case when x and y are independent. So this log ratio will be 0 when x and y are independent. In that case, p of xy will be equal to px times py. Otherwise it will be non-zero. In fact, it will be greater than 0. You average over all the possible values of x and y, so you take expectation with respect to joint PMF and then sum it over x and y. Okay, so this tells you about the information. Y contains about x and x contains about y. It is symmetric, you can clearly see, so it is same as I of yx. Okay, we also have proved that it is equal to h of x minus h of x conditioned on y, same as h of y minus h of y given x. Okay, this we have done. Now for continuous case, what will we do? We will replace this summation with integral. Very simple. And joint PMF, instead of that we will have joint probability density function fxy of xy log, always remember basis 2, then joint PDF here divided by the margins. Dx dy. Sorry, little bit of discussion here. Let's see. We can write it as, see, this joint PDF we can write as fx of x, right, f y given x of y given x log to the base 2. Here also, if you look at fxy divided by fy, this becomes f of x given y. Rather, it is more useful and more fruitful to take fxy divided by f of x, which is f of y given x divided by fy of y. See why I'm writing this thing. If you recall, I think introduced you to the notion of channel in the previous lecture, some of my previous lectures. I have told you that time that if x is the input to the channel, y is the output to the channel, x is characterized by some probability distribution. Suppose in this case it is continuous, so fx of x. Y is characterized by its probability distribution fy of y, although it will be unknown. What is known to you is also the channel. So channel will be characterized by conditional probability fy given x. So if someone tells you how channel behaves, it means you know the conditional distribution or conditional probability distribution function, density function of the channel. Given the input x, what will be the output y? What will be the likelihood of that? Okay, and fx is in your control. It is the input to the channel. You can control it. You can tune up the probability of different information symbols. So now you will be given two things. Fx is in your control, and someone will tell you the channel fy given x. Fy is not known to you, but we can express it. See how. Suppose we have a joint distribution fxy. You know that if I want from this joint distribution, if I want a marginal distribution of y, what should I do? In case of continuous, I should integrate it with respect to x, right? I will get fy of y. Or I can also express it as, I can write joint distribution as f of y given x times fx of x dx. Now you see a beautiful thing. We know conditional distribution because this characterizes a channel. Channel is known to us. We know what channel does with input. We also know this because it is the input distribution of input symbols. So now we can also compute fy using this. Now if you put this expression back, I can write I of xy as fx of x fy given x of y given x log 2 fy given x of y given x divided by integral fy given x fx of x dx. Now if we see this thing, it appears that mutual information is some function of two quantities. One is fx of x, the other is fy given x of y given x. Now see, out of these two quantities, see, mutual information, that is what Shannon gave a remarkable result, that mutual information is related to the rate at which we can transmit the information over the channel. And all of us want maximum data rates. You see, mutual information is about how much information y contains about x. Okay, so y is at the receiver side. So you would like that. He gave a very remarkable, in fact he proved it, that this correlation, that how much information y contains about x, if this is more, then we can transmit more number of bits over the channel, hence high data rate. And all of us want to maximize the rate, right? So he said that we want to maximize this capacity, we want to maximize this mutual information. But how can you maximize? We have only two parameters in our hand. One is the input distribution. This is the probability with which you generate the information. And the other is the conditional probability which characterizes a channel, which is not in our control. You don't know how channel will introduce errors, right? You don't know how channel is the whole space as well as the receiver part. Okay. So to maximize mutual information, the only parameter with which you can play is fx of x, right? And this he called as channel capacity. Now if you are given any problem over channel capacity, you will be given what is the input. You will be given, if it is discrete, you will be given the probability mass function of input. For example, if you have a very simple binary channel, so x can take only value 0 and 1. So someone may tell you that probability of 0 is p, and let's say q, and probability of 1 is definitely 1 minus q. So this q will be in your control. You can tune up that how many zeros will come out of a source or how many ones will come out of a source. Similarly, you may be given that what is the probability at the receiver you get 1 given you have transmitted 0. Similarly, probability you get 0 given you have transmitted 0. Similarly, probability that it is 0 you have transmitted 1. Similarly, probability that it is 1 and you have transmitted 1. So these are the conditional probabilities. This will be given to you, right? Someone may tell you to compute the channel capacity. What will you do? You will do very simple thing. You will express this I of xy in terms of px of x and py given x, right? And you will take this px of x, definitely this you will take as a variable. So you want to find py given x will be fixed. Px of x you can change this q, you can tune up, and you will maximize this I of xy with respect to q. Now this is in case of if you have a discrete channel. Okay, so we can have continuous channel, we will study that very soon. So now the only thing I want to repeat here is that in case of continuous variables I of xy, we can also write it as differential entropy of x minus conditional differential entropy of y, same as differential entropy of y minus conditional differential entropy of x. I want to recall that sorry, if you remember conditional entropy of y given x in case of discrete case, where x was characterized by probability mass function px of x, y is characterized by probability mass function py of y, and they are jointly characterized by joint distribution pxy. In that case, this conditional entropy was equal to summation over x and y. Here it was pxy of x comma y, and then we had log of py given x, y given x. If you remember this, you can go back to the notes and you will find it. Now in case of continuous case, what will we do? As usual, change this with integral. Instead of joint PMF, we will have joint PDF, joint probability density functions. Then same here, then instead of conditional PMF, we will have conditional fy given x, and we will have dx dy. This will be the relative conditional, sorry, not relative, differential conditional entropy. So far so good. And you know that we can also write I of xy as h of x minus h of x given y. Okay, now I think there is minus here. Yeah, there is a minus here, sorry. Now we will introduce a very important and most practical channel model, which is called additive white Gaussian noise, also called AWGN channel. This will be now very important model, not only for this information theory part, but our next topic, which is about bit error rate computations. So it is very important to understand it. So let me first see, let input be denoted by the process x of t. See, input process, it is a random process. Okay, so since again some of you are not from electronics background, they might not have heard about random process. So you can think of, you know now random variable, right? Random variable, you know. Now if this random variable changes now with time also, we will call it random process. A simple definition of it. It is a very complicated thing in one sense. It means that at every time, suppose you take t is equal to 0, you will get x of 0. This x of 0 is one random variable. If you take t is equal to 1, then you will get x of 1. This is another random variable. You will take t is equal to 1.5, you will get x of 1.5, another random variable. At time t is equal to root 2, you will have x of root 2. So at different times, you have actually a different random variable, and they may have different mean, they may have different variance. In fact, they may have different distribution at every point of time. then the process becomes very complicated. But we take very very simple processes where mean remains same, mean remains constant irrespective of time. So it means the expected value of this process at time t is equal to 0 is same as expected value of this process at time t is equal to 1, so on and so forth. This is one simplicity. The other is that if you take expected value between two time intervals, suppose x of t1, x of t2, then we say that it depends, it is a function of only the difference of the time interval. It doesn't depend upon what t1 t2 is, but it only depends upon t1 minus t2. These are the two assumptions we make about most of the random processes, and such random processes are called wide sense stationary processes. See the word stationary, why we use word stationary. If you see a general random process, so that at any point of time it can take any mean, any variance, any distribution. Now, rather than that, if you assume mean is constant and the correlation between random process at two different times, expected value of t1 t2, does not depend upon the absolute time, rather than it depends upon the difference between the time interval. In some sense it appears to be stationary, right? Not dynamic. That is a reason for it. So we will assume throughout that most of the processes we have, they are random. Now other thing we assume is not assume, that is what actually is done. We convert analog signals to digital signals, right? So we will study sampling later on, but right now I will like to say something about it. So here is x of t, it is a continuous time signal, right? We don't take its value at every point of time, rather than we sample it. And there is an important condition about the sampling, which says that if bandwidth of x of t is b hertz, okay, so in order to reconstruct x of t back from the samples, the sampling frequency must be at least 2 hertz. See, what does it mean? Suppose x of t is something like this. You want to take samples, okay? You want to take samples. Now if you take samples too far away, suppose here is this x of t, I take one sample here, I take one sample here, then you transmit these two samples, you will get these 2 points. From these 2 points, can we reconstruct the original signal? No. What you will do, you may join these 2 points, you can't get it. But if you increase the sampling rate, you take more number of samples, so then what we can say is you get this point, this point, this point, this point, this point. If you join them even by straight lines, you approximately get the similar signal. Now if you increase it more, right, if you increase more number of samples, take more number of samples, so you will get closer points, and when you will combine them, you will get it more smooth. Then what is the minimum number of samples you need to take? So that is called sampling rate, fs. That should be at least 2 hertz, where b is the bandwidth of original signal. So this result will be proved later on. Right now you take this result as it is. Now see, we have continuous process x of t, we sample it. So let's sample it at exact 2 hertz, which is called a Nyquist sampling rate. So today's lecture may be a little bit difficult for computer science, electrical background people. Although I will tell you frankly, in electrical engineering at NIT Srinagar, we teach communication system. There we teach sampling theorem. In computer science also we teach sampling theorem. So it should not be actually the reason, but I know some of you may not be comfortable. So you hold on for the sampling part. We are going to do it in detail in next lecture, in next chapter. Okay. So right now you just remember some facts. We have x of t, we sample it, we are taking samples of it, and we denote that by xk. Okay, where k is equal to 1 to up to some k. We take some k samples, and we are taking 2b samples per second. Okay, so this is the smallest permissible rate for a bandwidth b that would not result in loss of information. Okay, we will see this. Right now you take this as a result without proof. Now you are taking 2b samples per second. Now in t seconds, okay, what will be the number of samples? It will be 2b samples per second into t second, which is equal to 2bt samples, and this is what we call as k. This will be the number of samples in this time t. Okay, and here is the model for it now. So we have this xk. We will deal with sample it part. What happens with Gaussian channel, additive channel is, so here is this plus, here is a noise. Okay, so everything is considered in samples. So noise process is actually n of t. Okay, noise process, the noise which gets added is n of t. But since we are sampling everything, so its samples will be denoted by nk. Okay, so let me demonstrate it here. Suppose this is the noise. This noise gets added up to the signal, and remember that noise gets added up in communication system. Noise gets added up at the receiver. That is very important. At receiver, we have transistor as a part of amplifier, as a part of oscillator, as a part of demodulator, and it is inside the transistor that the random motion of electrons result in this noise. Okay, and you know the central limit theorem statement I have told you. Since lot of electrons are disturbing the incoming electron, so there are, suppose the incoming current is I naught, and inside there are millions of electrons whose current is getting disturbing this k is equal to 1 to infinity, I will write. So what is happening is this these are all random currents, and we are summing them up. So you know that sum of a large number of random variables, when we add up large number of random variables, their distribution appears to be Gaussian. We have, I think, shown you this result in the when we revisit the probability theory. Okay, if not, then you just inform me. I don't remember. If I haven't shown you, I will then show it in the next lecture. But right now, let's take a noise n of t. We will now sample this noise. Okay, we will sample it, and the resulting samples we denote by n of k. That is what we show here. At the output, we are writing yk, what we receive. Okay, now since in this channel model we have a noise whose distribution we assume as Gaussian, it is additive in nature. And one more thing, see, this noise will have some frequency characteristics, and one of the basic assumptions about this noise is that if this is the frequency, and if it is if on y-axis I plot the power density means power per hertz, then at every frequency it remains same, constant. If you compare this with white light, if you have a white light and if you plot intensity, versus frequency, we see that in white light, the proportion of every color is same. Color is actually related to frequency. So in white light, the intensity is because of all the colors, and that is same. So the intensity versus frequency of white light is constant. Same, we have assumption over the noise. The noise which gets added up at the receiver, that is Gaussian, that follows Gaussian distribution. But when we say in frequency domain, we see that if at every frequency the average noise power is constant. That is called power spectral density. Okay, this one, power spectral density. Okay, PhD. Now additive, this is the reason for the name, additive white Gaussian noise, AWGN channel. Okay, input x of k gets corrupted by a noise n of k. How it gets corrupted? In additive way, it gets added up. So your yk can be written as xk plus nk. Okay, now there is one important thing. This noise, although you are sampling it in time domain, you see here, but the values it can take any value. So nk is continuous random variable. It doesn't mean that we are taking continuous in time. No, what I mean is that if you take the samples now here, these are the noise samples. It is not restricted what values they take. They can take any values. You see, they can take any values. Same is the case with input. See, this is the input, we have sampled it, but it can take any value, right? These samples can take any value. They are not restricted to take any particular values. They can take any value. They are also continuous actually. Okay, so you have to understand this thing. One is the discrete time signal, but taking continuous values. Both xk and nk, they are discrete time signals. We are taking samples, but their values, they can take any value. See, this noise can take value root 2, it can take value root 2, it can take value 1.1, whatever. Okay, now you see, now the noise is white. White means its power density will be constant. So if this is the frequency, it will be constant. Now we are working, if you see, we are working in a particular bandwidth. Suppose bandwidth is b, so I will have a bandwidth b here and a bandwidth minus b here. Okay, that is how we plot it. So in this case, what will be the total power? The total power will be the area under this curve. Okay, since this length is 2b, okay, just to make it nice, we assume that the height is something n naught by 2. Why we take n naught by 2? Because I want this 2 and 2 to cancel out. So the total power of noise, average power actually of noise, is 2b times n naught by 2, which is b n naught. And if you remember Gaussian noise, so we assume here, so now this nk is Gaussian. Okay, we take its mean to be 0. Mean does not affect, mean is just a shifting parameter. We can shift it always, so not a big issue. Now what will be its variance? Variance of this noise, it will be expected value of, by definition, nk minus mu square, which is now expected value of nk square. This mean is nothing but it is average power. So this will be actually the variance, which we denote by sigma square, and that will be given by b times n naught. So this is now the variance of Gaussian noise. So now everything is clear. We can in fact write this fn of n. This will be the PDF 1 over under root of 2 pi sigma square e to the power minus n square by 2i sigma square, where sigma square is bn naught. Okay, now what we have is we have a discrete time and in fact memoryless. I will tell you what memoryless means. Gaussian channel. Memoryless means that if you have a symbol xk plus 1, at the receiver you have yk plus 1, yk plus 2, so on. So the next symbol does not depend upon previous symbol. That is it. That is what memoryless means. Okay, and also you will not be transmitting, you will not be using infinite power. You have a limited battery power. So your input, which is denoted by xk, its average power will be expected value of xk square. This will be the average power. Okay, and we assume that this expected value of average power, it cannot exceed some maximum power p. Okay, this is the average maximum power you can have. It is now power limited, definitely, because your batteries are finite. It will be power limited. Okay, now comes the, what is the amount of information, what is the rate of information flow? In other words, in this channel model where the noise is additive, xk is input, yk is output, what is the mutual information between xk and yk? Definitely you will write I of xk, right? And you want to maximize it. And with respect to what you can maximize it, as you know, input distribution, which is here f of xk of x, right? So this will be called the channel capacity of this Gaussian channel, and there will be a constraint that the input power cannot exceed p. In fact, what is the best you can do is you can take it equal to p. Okay, you can take it equal to p for all samples. Okay, so I will end my lecture here. This lecture is a little bit heavy. Give it a time. I will maybe have a doubt session also about this lecture, and then in next class we will derive the famous celebrated and one of the famous equations. So if you see, there are a lot of online stuff which write the famous equations of science and engineering throughout the history. In that, E is equal to mc square is there. Similarly, F is equal to ma is there. Laplacian equation is there. Bernoulli's equation is there. There will be this equation also. C is equal to half log of 1 plus SNR. This is the maximum rate capacity. We are going to prove it in next class. But before that, whatever I have taught today, kindly clear it. If you have any doubt in anything, try to search it online or any other books of BTech and try to get it clear. So next class we will inshallah prove this channel capacity theorem for AWGN channel. Thank you.